I think now we can start. So welcome everyone for this QISS Virtual Seminar. Today we are pleased to hear Ognyan Oreshkov, who is going to talk about the array of time in quantum mechanics. And so if you have short clarifying questions during the talk, you may ask them. Otherwise, just keep it towards the end in 30 minutes and we will have plenty of time to discuss. So Ognyan, it's your turn.
Thank you, Pierre, and thank you for the invitation to give a talk at this series of seminars. There has been actually a lot of interest recently in this very series in the question of time reversal symmetry, and I thought I would talk about it as I feel there are some interesting insights that can contribute to the subject. Before I start, let me just see first how to switch. So I guess I'll do it from here. Yes, so I just want to say that a large part of the subject of this talk comes from this paper co-authored with Nicolas Cerf that you see here. And the key ideas that I will develop were first introduced by Watanabe and Takharonov, Bergman, and Lebowitz many years ago. And my own ideas of time symmetry have evolved during the years and have been influenced by discussions with different people. And here I mention some of them who have had a recent influence on my understanding of the problem. One of the motivations for this question comes from this big open problem that we have in physics, namely the unification of general relativity and quantum theory. And in addition to all the technical difficulties that come together with this problem, there is also a conceptual issue at the heart of it, which has to do with the fact that in general relativity, space-time is a dynamical entity, whereas in quantum theory, in its usual formulation at least, a predefined time is assumed in order to formulate the very rules of the theory. And so it seems natural to expect that potentially seeing a way to go beyond these types of formulations of quantum theory can give us insight into how to merge these two theories of fundamental physics. And there are at least two ways in which standard quantum theory presupposes times in its formulation. The first is that, well, it talks about evolution in time, states evolving in time. You have unitary evolution of isolated systems plus random transformations upon measurement. And these same rules do not automatically hold if we switch the time axis, for instance, with a spatial axis, like unitarity, for instance. If you think about in quantum field theory, just exchanging these variables does not necessarily lead to unitary evolution in a space-like direction, time-like hypersurface. And so you see that these very rules already presuppose a time axis, to put it in the context of space-time. On top of that, you have these probabilistic assignments that are, at least at face value, time asymmetric. So normally we talk about probabilities for outcomes of future measurements given past preparations, which are given by the Born rule. And this same rule, if you think about it backward in time, it does not appear meaningful. And this was raised by Watanabe and Takharonov and many other people. And this is what I would like to discuss here. This is, of course, disturbing because if we expect fundamental laws to be covariant with respect to time reflection, which is true for the Schrödinger equation, for classical mechanics. So it raises the question, what, if any, is the problem with the Born rule? And as I will argue, a proper resolution of two can also offer us a resolution of the first issue. So it can allow us to formulate quantum theory in meaningful operational terms in a way that does not presume distinctions between space and time. And I will use a setup that was introduced by Watanabe when he analyzed the question of time reversal symmetry to also state what the Born rule is. So he was imagining this setup in which you have two agents, Alice and Bob, who perform standard von Neumann projective measurements. and yes, we imagine that we have a task, prediction, in which, given knowledge of the outcome that Alice observes I, she tries to guess J. So they know which kind of measurements they're doing, and they want to, she wants to predict the outcome of Bob. And this is famously given by the Born rule, which is written here. And I would like to emphasize that, as far as we know, this is the best prediction that Alice is able to make, given all the resources available in the universe at that time. And this probability is furthermore unconditionally true. It's unconditional on any variables. This is an absolute statement about these future probabilities that we believe holds. And as far as we know from experiment until now, there has been no way, there has been no violation found. You may similarly ask the opposite type of question, which would be retrodiction. Imagine that now Bob looks at his outcome, J, and wants to guess the outcome I. So what is this reverse conditional probability for I given J? Well, from the forward one, you cannot immediately invert because you need to know also the probability of I. And we know that in general, one could calculate that using Bayes' theorem, but the probability depends on the initial state that Alice receives. Okay, at this point, and of course, the Born rule back in time, as was observed by Watanabe and Haronov and many, many people, is recovered when the initial state is maximally mixed. So if the state on which Alice operates is maximally mixed, we get the usual kind of the same rule back in time. So does this mean that the Born rule does not hold backwards in time in general? And to answer this, we need to first clarify the circumstances under which the Born rule is supposed to hold in the first place, right? It's a rule, but one needs to specify in which circumstances this rule is meant to be applied. What does it mean? Remember that in the conventional time direction, the rule holds unconditionally. And of course, it could be trivially extended to allow conditioning on some past or present variables. This is what I said, that given any resource present in the universe, you could not possibly predict the future outcome better than the Born rule. But if you allow this type of conditioning, this immediately can be seen to fail backwards in time, because if you start allowing conditioning on future events, you start getting all these post-selected situations in which the Born rule can be seen not to hold. So, but you may still ask, okay, maybe it still holds backwards in time, but unconditionally, just like it holds forward in time. And its apparent failure when the initial state is other than the maximally mixed state is simply due to the fact that these cases are defined conditionally on some variables, like the memory of someone who prepared the initial state. Now, this is my understanding of this recent proposal by Di Biagio, Donna, and Rovelli. Please, the authors, please correct me if this is not a correct interpretation of your suggestion. Is this more or less an accurate understanding of your idea, the sense in which the Born rule you claim holds in time? Are you asking your question? You want a short answer? It's a question, yes, please. If you could, I mean, maybe you're not certain. Maybe I expressed it in ways that don't correspond to the way you think about it. So if that's the case. Yeah. So my short answer is, I guess, yes. I don't know if Andrea or Peter presented what is it more. The only point is, the only slight bemol is that I wouldn't see it as a proposal. I would just see it as something that has been said many other times, and we just sharpen and focus, but it's not a new proposal. It's just our understanding. Definitely, yes. But there was this paper in which you analyzed. Yes, and, statement, yes. Yeah. Okay, so I also want to. And I would also like to mention, yes.
I would also add that the Born rule towards the future doesn't hold unconditionally. It only holds if you're conditioning in variables in the past or the present. And the time reverse of that is that it would hold the past Born rule holds unconditionally if you condition on the present or the future.
I'm going to discuss this next. Yes, I will discuss this next. I do believe that it holds unconditionally also in the future. When I say unconditionally, of course, what I meant unconditionally, I mean unconditionally on any other variables, like the preparation of the state is taken, the measurement that will be applied is taken, but no other variables. Provided that these two things are given, there is no implicit conditioning forward in time on anything else. You may add it, as I said, but you don't need to. And I will actually explain this in greater detail. Here, I would also like to mention the work of Lucian, since closely related. I'm not sure if he subscribes to the same interpretation. But I mean, what I will say in this talk is that I will argue now that this is actually incompatible, that this postulate is incompatible with the possibility of having memory. Yeah, this is, I understand, probably controversial, but I will try to prove that in great detail, adopting a specific way of thinking about quantum theory. So before I go on to argue, I would like to just clarify, to remind us a few basic concepts in probability theory, which I will illustrate here with assuming some setup, like a setup in which you have some local random variables in space-time. This is simply because we anticipate we'll be talking about local experiments in the space-time later, but these are just some random variables. And imagine that we can assign a probability distribution, P of x1, x2, etc. on these random variables. Now, this distribution, by definition, is unconditional distribution, but we can use it to derive conditional distributions, such as, for instance, the probability for xj given xi, and we know how to do that. Given a joint distribution, you can calculate the marginals, you can divide and calculate anything. But within the context of the variables I specified, this full distribution is unconditional. It could be conditional on some other implicit variables, but here this is what we mean by unconditional distribution. Now, of course, in the context of our discussion, the physical theory may prescribe quantities such as, for instance, the probability for like the probability for xj given xi. You know, in this case, this distribution will be said to be compatible with the theory if it yields the prescribed quantities. Now, another concept I want to emphasize, another concept is the prior and posterior distribution. So for an agent who assumes this distribution can play the role of a prior from which they can calculate posterior probabilities upon evidence. Like, for example, imagine that the agent observes the value of the variable x1 to be here denoted by small x1. Then they will update their assignment correspondingly, like this probability will become like a delta, Kronecker or delta function. And yes, and the probabilities for the rest of the variables will be updated accordingly, starting from this prior. And what I here want to stress is that prior or unconditional probabilities, they do not need to be uniform. In fact, they very rarely are uniform. Prior probability, if you start with uniform priors, you cannot do any interesting inference. So what this means is that in this context here, an assignment of a non-maximally mixed initial state does not mean that the assignment is conditional on any physical variable, such as the memory of anybody. Here we talk about states. Before I talked about variables, you may imagine that there is a preceding measurements. There are preceding measurements, and if you were to assign on these measurements, you know, a uniform distribution, that's equivalent as if they were applied on a maximally mixed state. And if you don't know the outcomes, you would say here it's a maximally mixed state. But if you don't assign that, if you assign a different state, this does not mean that this assignment is necessarily based on evidence. Okay, so this is my first point. But nevertheless, we may still demand that the Born rule holds unconditionally back in time. In other words, we may want to postulate a suitable prior. And I claim that. Yes.
Yes. Just a quick question. Do you agree that in all the experiments you're describing, the evaluation of the experiment and whether the Born rule was correct or not is something that takes place in the future of the experiment? Both the prediction is made in the past and the experiment is in the past, and it's only when you have both the data from the experiment and the prediction from the past, so you are in the future of them, that you're in a position to evaluate the experiment.
So yes, I agree that within the experiment we imagine performed in our world, that would be the way it would be done. But I do not think that this is essential for the argument. So we may not specify a priori where exactly this information processing is going to take place. As I will show, it is possible to conceive worlds in which information is going to go back in time, for example, and someone can have memory of future things and do all this reasoning later, for example. So that, I think, is not essential for the moment. But indeed, in the experiments, I envision what people would actually do in our world, that would happen in the future, yes.
Okay, thank you. But are you seriously imagining that there are worlds where that is not the case?
I'm seriously imagining this, yes. I'm imagining because I show that they are logically possible. I don't think that, I don't know whether our world is one of them, but I believe they are logically possible. And I will give some examples maybe. I did not put slides specifically on this, but it will, I believe it will become clear.
Okay, thank you.
Okay, yes, so here is basically the claim and kind of the rough proof that I present, and I'm going to give a more detailed version later. But basically, the claim is that assuming that the observers are physical systems, and observations such as the reading of a memory corresponds to a quantum measurement on a given system or subsystem of the agent, this would be incompatible with the possibility of local agents having any non-trivial knowledge about other systems at a given time, as well as non-trivial memories. And the proof is extremely simple.
Short question. By non-trivial knowledge, you mean certainty, or you mean also probabilistic knowledge?
Probabilistic.
Okay. Thanks.
So if the time reverse Born rule holds universally for all systems, as it was in an unconditional sense, as we discussed, then the prior to evidence state of the universe at any time would need to be assumed maximally mixed, because any subsystem would need to be fully unknown, which in particular implies that the evolution must be unital. Now, so this is like a prior in which at a given instant of time, an agent is going to go and look at specific variables, and then they will infer from this prior knowledge about the past, the future, as well as possibly space-like separated regions. Now, since all these separate subsystems are uncorrelated, an agent who observes a given local system at a given time cannot infer anything about other systems at that time. They're totally uncorrelated. Now, this in particular means that they cannot also have memories, because if you imagine a past von Neumann measurement of the kind we were discussing, where you project the system and immediately after the measurement, the state of the system is correlated with the measurement outcome. You get a contradiction if you assume that, basically, because right after the measurement, the memory or the register where the record of the outcome is stored would need to be fully uncorrelated with the state. Therefore, no agent could possibly can possibly read out. It need to be you would need to have correlations, but in practice, as we just argued, such a correlation is not part of this prior state. So, in other words, like to read here, you cannot have memory of the outcome of a past von Neumann measurement, since the state of a system should be correlated with the outcome. And so you cannot imagine that you have this situation at all at any time. So I'll give a more detailed proof of this argument later with more general quantum instruments in the framework that I would like to present. But basically, as I see this argument, it says as the Born rule, the postulate that the Born rule holds unconditionally back in time is inconsistent with the belief that we can have memories of the past. And I emphasize here the word belief, because this is one of those things that we cannot actually prove. I mean, this is, there are these in epistemology so-called foundational beliefs that you cannot derive from anything else. I believe this is an example that we all have these beliefs that what we experience now corresponds to something that has happened outside of us, that there is an external world, that we have memories, and they correspond to what has actually happened and so forth. I find it kind of interesting that here we see the possibility to actually postulate a prior, and one always needs to assume a prior in every of this probabilistic reasoning, or this its kind of modified, developed version in the context of operational probabilistic theories. You seem to need to start from a prior, which is an assumption that cannot be actually derived. And I find it very nice that here we see direct link to one of those beliefs that one can never prove or falsify. So this is the first message that I wanted to make. Now, so how can we save then time reversal symmetry? And I want to discuss this proposal that was due to Watanabe and Aharonov, Bergman, Lebowitz, and later slightly, let's say, modified version, a bit more general version that I'll present. So their proposal was, okay, I mean, if you back in time, you have these different cases of initial states that may arise. And so let's just consider a rule that holds in all of these cases. So basically what they proposed is to postulate a different, much more relaxed rule that says it's about probabilities between pre-selected state in the past and a post-selected state in the future, which is what they call the two-state vector formalism, or a different name by Watanabe. Essentially, you know, you consider, somehow interpret it as if having these events, or maybe it could be even the trivial event in the past leading to a state, your assignment or your belief about what's happening or what's implied by these events. You know, you think of them as kind of coming from the past and from the future, and you say that, that you should define the probabilistic rules in this way, conditionally on this pre and post selected states, the two-state vector formalism, and they postulate that this is the main rule. You can write it in a mixed state version. It looks something like this, and of course you get the predictive Born rule when you here have the kind of maximally mixed state coming from the future, or the predictive Born rule, like we said, if you have, you know, a maximally mixed initial state. Now, there could be immediately some natural concerns, and I must tell you that the first time I learned about this formalism, I had a very negative reaction. For various reasons. It's just, first, somehow the rule doesn't seem very nice, let's say. It's not linear in the state. We're used to be linear in the density matrix. Then the probabilities for a given outcome depend on other possible outcomes. There's some form of contextuality in the probabilistic assignment, which seems totally kind of different from the way we used to use in quantum theory. Then it's also unclear in which sense the forward and backward evolving mixed states, let's say, are mixtures of pure states, because standardly a mixed state is a probabilistic mixture of pure states, but here the coefficients are not probabilities, except in situations where the Born rule actually applies. And then why is the Born rule always valid for prediction, unconditional on subsequent events? And how is this linked to the anti-unitary transformation of time reversal? There are many questions that arise, and I would like now in the remaining to argue that I will not go in great detail, but I'd like to argue that this is fine. All of these things are fine, and it can be done. And it's these properties, in fact, some of these that seem concerning are quite natural, considering the philosophy behind this rule. So I found it particularly to understand these questions. I found it particularly kind of insightful.
May I ask for clarification?
Yes, please.
It seems, first, I'm not sure that Watanabe had what Aharonov had, but in any way, what Aharonov had, it's not any kind of postulate. There is nothing but standard quantum mechanics. It's just a realization that given you information about two measurements, T1 and T2, and to describe measurement in between, you have the ABL formula. There is no any postulate, there is no any new theory. And you said that you liked it, not liked it. It's kind of strange for me. It's just standard quantum mechanics, but the way to see new things inside standard quantum mechanics. It's not a new postulate.
Well, any theory has a set of rules that are postulated, and if you adopt the two-state vector formalism in its pure form without the extra condition that in the future you should have this kind of very mixed, maximally mixed state, then I mean it is a postulate, and it's a postulate which is specified to apply in a specific context. Of course, we derive it by Bayes' rule from the other thing that we know is true. The other thing was also a postulate in another way of thinking about quantum theory. But here, for example, this theory does not tell you that necessarily you must have the future to be maximally unknown. That does not follow from this rule as such. Okay, so if you like, you may call it derived. Yes, it is derived because they did not invent it out of nothing. In this sense, it is kind of a postulate in your theory, after all. It's a main probabilistic rule that you should use to make predictions or retrodictions or probabilistic assignments. It is this sense that I meant it. Now, about whether Watanabe had the exact same thing, he did not have the exact same description. He also introduces some kind of vector with that there is some differences, but he does have the main formula in the proposal that the initial and final state we should condition on them to calculate intermediate probabilities. So I believe this is the same idea. At least as far as the quality of the idea is concerned, I believe that's a fair statement. Okay, so I specifically found, in order to understand these issues, I found it particularly insightful to think about quantum theory in this operational language that has been developed, pioneered by Ludwig, perhaps maybe even people before him. And specifically, I'll talk about the so-called circuit framework for operational probabilistic theories, a term that was coined by Kiribella, Dariano, and Perinotti in their reconstruction of quantum theory. But this same idea was first, can be found also previously in Ludwig, as well as it was introduced maybe simultaneously with Kiribella also by Lucien Hardin. It's very important that it's based on joint probabilities. This is the reason why I don't mention here other people working on generalized probabilistic theories. But it's a way of thinking about quantum theory in which your fundamental concept is that of an operation or test, which is basically a set of possible events from an input system A to an output system B in general. This does not need to be quantum theory yet, but we are going to specify to quantum theory in this language. Then an important ingredient is the idea that you have the so-called trivial system. So you can define operations of this kind that have the trivial system as an input, so no input, as well as these operations that we call measurements, no output. These things can be composed in a sequence in parallel to form circuits. And the key idea here is that given a circuit with specific operations, the theory will prescribe joint probabilities for the outcomes in a circuit. So by definition, here, this is a very important concept. By definition, a circuit is something, is an experiment for which probabilities can be assigned. Because it may be that you have situations in which you cannot assign probabilities. For example, you perform a measurement. What is the probability for a specific outcome? Well, unless you tell me on which state I apply it, or unless I make an assumption about the state on which I apply it, it's an ill-defined question. So you need to always close a circuit to get valid probabilities. And the way to interpret these objects here, a circuit, is that somehow it formalizes the idea that systems are the carriers of information that establish correlations between events. So here, if you think these are events of some kind, when you draw this picture, you're claiming that all these correlations that you see between them are due to these systems here and nothing else. Now, this is one can equivalently express a theory by saying what are the joint probabilities for preparations and measurements, basically. And however, when one constructs such a theory, one assumes equivalent classes of operations as well as of individual events inside the operations. And those are called, for preparations, these are states, effects, for the effects are for the measurements. The equivalence classes of measurement events are called effects. And then you have transformations for general operations from input to output system. And once you take these equivalence classes, you automatically get this sort of non-contextuality, because the joint probability for a preparation and a measurement becomes a function of the state and effect only, right? And this is important. Later you will see that actually the ABL formula or this other formulation that I will develop is, in a sense, is non-contextual. It's non-contextual by definition in what are the actual state space, in what is the actual state space and effect space. Now, the standard time asymmetric quantum theory in this language is basically the following. These operations are just quantum instruments, a collection of CP maps, completely positive maps that sum up to trace preserving maps. Then a preparation can be, through an isomorphism, it can be represented as a collection of positive semi-definite operators that sum up to a density operator. The measurement in this language is a POVM, a collection of possible positive semi-definite operators that are a resolution of the identity. And then the main probability rule between states and effects is just this rule, which in the case of deterministic states rule, you get the Born rule. Now, it was observed by Kiribello, Dariano, and Perinotti that there's an important property that they named causality axiom, also observed by other people. Also, it's in Ludwig, previously also recognized as a kind of interpretable as causality by David Pegg. Is this property that when you consider a preparation and a measurement connected together and calculate the joint probabilities, they have the property in the standard formulation that the marginal probabilities for the preparation don't depend on which measurement you put here. And this follows just by the fact that when you sum up over EJ in standard quantum theory, it's always the identity matrix. So you get the same for the probability of a preparation outcome. Now, mixed states are, when you have this property, you can actually see that mixed states should be probabilistic mixture of pure states. So we were thinking along these lines and trying to kind of recast somehow to come up with a good motivation for first to understand where this causality comes from, why does it seem asymmetric, and also to see how to recast these formulations of quantum theory in time-symmetric language. So I will not go in discussions of this one can find in this paper, but mostly in the appendices or supplementary information, in fact. Some philosophical considerations about what is actually an operation. And roughly speaking, the main idea is that one of these things that we draw in boxes is really describes knowledge or also belief, could be unconditional or prior belief, about the set of possible events in such a box. And one observation we can make is that in the standard formulation of quantum theory, this knowledge is assumed unconditional on variables in the future. In other words, operations in the standard formulations are presumed realized or defined by procedures that do not involve post-selection. They're only like you prepare your apparatus in advance, you set it up, a magnet or something like that, and you let it run, and only then you can go on and find out what is the outcome. But you would not say that after you have found the outcome, you have done the operation. This is not what enters in this formulation of the theory. You wouldn't call a projector on a given state an operation that an agent can apply, or it is considered an outcome and not a full operation. And that is because actually in practice there seems to be a constraint on what we can do without post-selection. In other words, this causality condition expresses a constraint on operations realizable without post-selection. And one can quickly see that the same condition would not hold under time reversal, because the pre-selected operations in that direction are post-selected operations in the forward direction, and the post-selected ones, they are not the same. And one cannot, it's been shown actually in the literature more rigorously that there is no kind of reversible mapping between the two sets of operations. So in other words, physics under time reversal is not described by the same operational quantum theory. And so what we may propose is, which is in the spirit of Aharonov and basically the same idea, but at the language of operations, is to allow operations to be defined by both pre and post selection. So in other words, we adopted, I see this, the motivation informational somehow in spirit. As I told you, an operation describes knowledge or belief of an agent about the set of possible events. And here we just say that, okay, operation is this description of possible events in a given box, conditional on, I say here, conditional on local information. This is very important because if you condition on knowledge of the state on which you apply this operation, then this doesn't make sense. I will not go in details, but can explain later if you want. So the whole idea is it may be realized by post-selection, it may be realized by pre-selection. We don't even need to specify how it's been realized. The point is that it is your knowledge about the possibilities that can arise in this region. And one can immediately, just by using Bayes' theorem, kind of calculate what the new theory is going to look like. You have this basic probability rule now for states and effects. It's just if you can see, now the difference is that these EJs don't need to sum up to the maximally mixed state as in the standard quantum theory. We nevertheless can choose a normalization, but only of an overall constant, because this is irrelevant for the probabilities. And remember, we take equivalence classes. So I choose this normalization to keep it close to standard quantum theory. And this, in fact, this rule has been previously discussed in the context of retroduction by Peck, Barnett, and Jeffers, and one can postulate it as the rule. This is the rules of your gain, and this is the prediction. This is the main probability rule. Now, I want to emphasize here by rho bar, any bar, we define this kind of the average, let's say, density matrix, or average is not a proper word, but really the sum of these things that can come out of the preparation appears here and here. This is important because if you want to calculate what are the states and effects of your new theory in the sense of equivalence classes, then you see that from this rule that actually these two operators are important in defining equivalence classes. Similar, so you would say, strictly speaking, that your states are this and effects are this. I will not actually use very much this because it's a bit not very elegant, let's say, this representation, but it's useful to keep it from time to time to remind us that actually the equivalence classes are different from the standard theory. And one can see again the states and effects as functions on each other via some rule like this. When the denominator is 0, there are two options I see. You can either say that it's not defined, or you may kind of trivially postulate some extension for this function. Yes?
Do you think that you can soon conclude?
Do I think it what? I'm sorry?
That you can soon conclude your presentation? How much time do you
Yes,
need?
I will try now in 5 minutes to go very quickly to the rest, because some of the most important ideas are actually still coming. I will attempt. Yes, it's been 40 minutes, so I will try to finish quickly. Okay, just to say, this is a more relaxed, this is less constraining theory. By definition, by the rules of the game, it does not imply Born rule must hold forward in time. It implies more general types of unconditional evolutions could be possible in the universe, not necessarily unitary, but something like post-selection, but it could be unconditional because the rules permit it, and more general symmetry transformations, including even a more general description of time reversal symmetry. Now, about time reversal, I think I'm going to skip that, but essentially we analyze in this paper how to think operational of time reversal as an active transformation in a certain sense. So you should not, when you see such a circuit, of course, back in time, you can always interpret it because it abides by the same rules, but rho I is not necessarily the measurement that you would see if you had time reversed something. So there is you can define it as playing a movie backwards, like if you have a preparation procedure. If you see how it looks under playing it backwards, it will give rise to something like a measurement, but which measurement it is, you need to define it, relative to which to preparations that have not been time reversed, and so forth. So we analyze this, and we derive more general symmetry transformations that this theory permits. In particular, time reversal is in a class like this, where states go to effects, effects go to states. Strictly speaking, this is not, when you distinguish the two spaces of states and effects, in fact, you see time reversal is a linear transformation. It could be unitary, but it becomes antilinear when you represent the states in the effect space via canonical isomorphism. But this canonical isomorphism is not, is an arbitrary choice, in fact. We discuss all of this in these papers. And so what I want to come back to now is, again, this important question. This is about understanding, actually, memory arrow and things like that. So, so I come back to, assume that the universe is given by, is governed by unitary dynamics. Okay, so this means that every operation that takes place in some kind of region of the space-time could be dilated to a unitary evolution that involves the devices and environment, such that the outcomes of the operation are moved to measurement outcomes on the past and or future boundary of a possibly larger region. So this is like moving the Heisenberg cut. So here is the assumption I make in this analysis. He said that, that the universe between two times then can be modeled as follows. So you have, if you can imagine the full quantum field theory, there is like some unitary evolution going on between two times. And as you need to close the circuit, you put preparations and measurements on the past and future boundary. And all the outcomes of things that observers see, like inside the bulky part, are consistently mapped right here. So there are no Wigner friends in this analysis. It's important to stress that now these are like boundary conditions here, but they are necessary. They are necessary because, remember, you need to have a closed circuit in order to prescribe probability. So we need to specify something, and that is not given here only assuming unitarity. Nobody tells you what this must be, and this is like a de facto thing that you end up finding, like every initial condition in, say, in classical mechanics. Now, this circuit yields prior probabilities, which are not conditional on any event in space-time. Now, consider an observer in a local region who measures variables in this region. Now, they are performing something like a quantum instrument. By the assumption that they can be embedded in a unitary, I can dilate this and describe it by something like this. Here, for simplicity, I have imagined that the outcomes are moved to the future boundary. But this formalism is compatible with imagining joint outcomes on the past and future. But here, for simplicity, and I think this is enough, because what I want to show is that I will show that such an agent will predict only future circuits that respect causality out of these boundary conditions. So basically, this circuit must be consistent with the full unitary circuit. So you can imagine extending it to the rest of the universe somehow. Here I've put some unitaries and something. If I still move this further into the future where I was putting the boundary condition, this was just a choice. You can always move these boundary conditions back and forth consistently with the unitary dynamics. Here I have moved them to the future. Here, this projector is going to get mapped onto some kind of delocalized version of itself through the unitary dynamics, which is the version of what Alice sees. And I'll consider the future evolution according to Alice, excluding the image of her own observation. This is important because I want to argue that she can only predict standard quantum circuits as a consequence of special boundary condition here. But of course, if you measure something, you can infer that this something will propagate into the future, and you may say, well, I'm able to predict a future outcome, which is like in violation of a Born rule. But this is trivial. This must be excluded. This is what we did not do in the paper with Nicolas Serre, and this is the kind of an update, which I think is a very important one, that to properly do this argument, you need to do that. And then I claim that all effective future circuits that Alice can infer based on her knowledge of this outcome pk will consist of standard trace-preserving quantum instruments, if and only if the sum of these guys here is the identity matrix. And the proof is very simple. You can calculate what is the updated circuit for Alice given this knowledge. It's going to project something here. It's going to maybe update the initial state. So you get a preparation followed by a unitary, because all these other systems, excluding her own image, evolve, are isometrically mapped into the future, followed by this measurement that happens in the complement of this. So, and it is well known that anything that you can get as an effective circuit from this type of evolution consists of standard quantum instruments. And vice versa, if the future boundary condition is a standard POVM, you can, anything that an observer can infer consists of standard circuits. Sorry, here I was, previously I showed the one direction, like if you have this boundary, if you have this boundary condition, Alice would infer standard circuits, and now I'm saying that vice versa also holds. So here now the time is getting a bit tight, but okay. In the opposite direction of time, it's an analogous situation, and this means that if we think we can infer the outcomes of past operations, as we do believe, then if you think in this language and want to be consistent with this picture, then the past boundary condition can all be assumed maximally mixed. So moreover, it's also known that if I assume a different than maximally mixed boundary condition, I can model situations in which I can remember things. Our prior circuit then, at least to describe what we observe currently, has this form. Similar ideas in the context of consistent histories has been also, I found out, have been discussed. I don't know exactly how they relate in this circuit language. And I think maybe I should leave this for the discussion now. I think it's one of the most kind of interesting things about memory and causation.
Yeah,
but
I think you should try to conclude soon.
Yes. Okay. I will actually. I'm going to ask this question, and then during questions and answers, we can actually go and discuss this. So, one question is: can these boundaries conditions account for the errors of memory and causation? And I will argue that they can, and without any use of thermodynamic arguments, in fact. Finally, I'll just say that by introducing a suitable, I'm going to skip through the final slide. Basically, by introducing a suitable isomorphism that depends on time reversal, one can recast quantum theory in a totally time-oblivious fashion, where you just talk about regions that are connected in a certain way, and you have these positive semi-definite operators, and there is this rule, again, with the denominator, which you would use to make predictions. This is very akin to the Robert Ocker's boundary approach to quantum field theory, expressed a little bit in a circuit framework, allowing outcomes also to be in the regions. And yes, thank you very much for your attention. Here I just leave the summary of my talk.
Thank you very much, Ognyan, for your talk. I invite everyone to use the Zoom icon to clap your hand virtually. And now it's time for questions. So if you do have questions, please raise your hand and then pick up your voice. So I see Carlo, you're first. So please go on.
Okay, thank you, Ognyan. This allowed me to try to understand a little bit better what the kind of things you're saying. I have two questions. Pierre, stop me if there's pressure. I should stop it and remain to one. So the first is specific, the second is general. And the first is that somehow you did two things in this talk. In the second one, you presented this sort of extended formalism that you worked on. At the beginning, however, you had the first part in which you said that if the Born rule cannot be applied to the past, there is a theorem, and the theorem says that memories are impossible. And then you sort of flew up through the argument or the proof of that. Mm-hmm. And I don't understand the theorem, or I don't believe the theorem if I understand it, because I don't understand what you mean by memory there. Mm-hmm. In the following sense. There is a very simple fact that we know a lot of things of the past because they're determined by things we see in the present. And very simply, quantum mechanics, we know in some limit gives classical mechanics. And just using classical mechanics, you can see that some things were true in the past. Mm-hmm. So unless you have a sharper, so if by memory means knowing something that happened to be true in the past, I don't see how can this be true. If a past quantum event determined something to explode and or something to fall, and I see the outcome of that, So I don't understand what is the definition of memory here, and to any definition that I can imagine, this seems very implausible to me.
Okay, so here I have I had to skip this part. Do you see my slides still?
Yeah.
Yes. So here I discuss memory, specifically our human memory, the type of memory that we think we have to some extent in this language, which concerns a classical world.
No, but wait, this is not the memories in your formalism. It's, you present a theorem before introducing your formalism. So I might understand that within your formalism you can define something what we call memory, but what was the memory in the theorem you gave before introducing your formalism?
Maybe I did not. I do not give a general definition of memory, but I give a specific definition of memory which fails, which I believe is accurate for our memories, and that is, I believe, is sufficient for this conclusion.
So what is it?
But I can give a general definition. It is
the one of the theorem, the one that allows you to derive a theorem. What is it?
Here it is. So here I'm discussing this. I was talking in my theorem about memories. I specifically talked about the memory of the outcome of a von Neumann measurement. So that is what I meant there. But I would like to argue that essentially this is pretty much captures what we mean by our memories or macroscopic memories that are of concern to us. Because our memories concern observations of approximately classical systems, right? Which means we observe them without significant disturbance. So you see something, you don't necessarily change it. And that means that reading out of a memory in this language of circuits in quantum theory corresponds to reading out the outcome of an approximately projective quantum instrument, right? Because if you want to model how you you project, this is the way to model an observation of an approximately classical system that you don't disturb. I mean, it's more or less in the subspace in which you project, so you don't really change it, and it stays as you see it. That's kind of our interpretation. Like what I proved is that it is impossible to have an observer who, by performing a local measurement in his self or in his surroundings, immediate surroundings, or in his brain, to infer or to infer the outcome of another measurement that you imagine has happened just a minute ago on another system.
Wait, how is this possible? I mean, I go to Fabio Sciarrino laboratory, ask him, oh, yesterday you measured that spin, did you get up or down? He says down. And now you say, that my quantum mechanics implies that this is impossible. Why?
Well, I'm saying that if you want to be consistent and thinking that this process of what you remember and so forth is described by quantum mechanics, you must assume that there was an initial state that's different from maximally mixed. Think about what is the way you think about memories. You initialize a memory, right? And then you read it later. If you don't know that it was properly initialized, when you read it, you cannot know that actually it faithfully represents what happened. But how do you know that it was properly
quantum mechanics is classical mechanics. So I just track back classically. I mean, I am classical, Fabio is classical, our voice is classical. So why do I need to, and I just simply have to believe that as long as, effects are larger with respect to h bar, classical mechanics good enough approximation. So I can just ask him what was the result of his,
But in classical mechanics, you also need to assume that you know some initial state, really, of yourself. Like, how do you know that you were properly initialized, that the classical camera was properly initialized? You need to say, oh, I know it because I remember I measured it before, but how do you know that this memory is faithful? This is infinite regress, as far as I can tell. So there is this assumption.
It's very cute to say to Carlo, are you sure? But in fact, I think Carlo is right. You can say, well, there's this little problem and that little problem, but overall classical memory has to be precise, whatever your definition of precise is.
Yes, it is. And here it is completely like I can model this memory fully, just imagining an initial state, let's say kind of low entropy or any other like a pure state that evolves, and you can completely consistently model classical systems as a special case of this general theory. Like you can, there's nothing, classical mechanics can be understood as a limit, as an approximation within quantum theory, and this we know very well. So I don't see any kind of logical contradiction.
Let me go to the general question, the second question I have. This is general, and somehow I want to see what you think about that. You somehow the logic of what you what I understood about your presentation. First, you said no, quantum mechanics cannot be viewed as time reversal invariant in the sense that you were saying. Then you said, actually, I belong to a community that think in quantum mechanics in terms of some peculiar probabilistic theory, operational ways, Alice and Bob, and this or that. Which, of course, it's a super interesting way of looking about quantum mechanics, but it's not the way many people look at quantum mechanics in other area of the huge space of physics. But it has its strength. And then you noticed, and I think I fully agree, that in sort of the very foundation of this operational way of thinking quantum mechanics, one thing about agent, and you assume that an agent has a time orientation and given something, ask questions about the future, fine, and we are with us. I'm with you. And then you said that you developed, in fact, much before the current discussion that of the papers of ours and others that you mentioned, that you had developed a generalization of that framework, where you have the language for talking about sort of quantum mechanics in a generalized sense within this operational language. And Lev Weidman, with whom I was a good friend, but I very often disagree with him, made a comment which I actually agree entirely with him. He said, well, look, that way of viewing quantum mechanics where you actually make prediction equally based on some knowledge of something in the past or something knowledge in the future is not a generalization of quantum mechanics. It's just what quantum mechanics is. Now, this is a matter of words, because of course, what quantum mechanics is, we don't have an academy that states what it is. In some books are presented in a time-oriented way, in other less. So if you want to say this is a generalization of quantum mechanics, okay, it's a generalization of quantum mechanics. But then we're not saying very different things. I mean, there is a way of looking at quantum mechanics in which you can, given information about the future, call it post-prediction, call it the way you want, you get information about what happened before, and another is time reversal. So the theory itself is it's not time reversal, it's time reversal invariant. Now, of course, we live in a world which is highly time-oriented, because entropy goes up and so on and so forth. And we can justify it, describe it very well by making some assumptions about the past state, which somehow the past states, whereas David Albert past hypothesis in one way or the other, or whether it's a standard assumption that entropy was lower in the past, the way you want to frame it. It is a fact that our world, including the agent, including the memory, including the fact that we don't know the future, we know so much about the past, is related to some asymmetry in the boundary state of the world. That's I would say is a common story in thermodynamics, which are recovering in a quantum domain. So where is the actual difference? At some point, you seem to have said, and this gives some truly new phenomena that somehow seem not to be predicted by quantum mechanics. Aren't we, after all, agreeing and just using different languages for saying the same thing, namely that the dynamical theory itself, it's time symmetric, but the world in which we live happened to be in some situation that seem to be easily described by a preferred relatively simple, in some sense, state in the past for some reason we don't understand well.
Mm-hmm. Well, the way I see the difference, first, just to clarify that the sense in which I say this is more general theory is merely because a theory is defined by a set of rules that tell you things or you put constraints on certain possibilities, but it is this by definition concerns certain scenarios, okay? And so this formulation that I present is much less constrained than normally, because it does not, in any way, you cannot infer from it that you must have the Born rule holds unconditionally forward in time, as is the case in our universe. Other time asymmetric formulations put this as a postulate. You can put the causality postulate, understanding that we're talking about pre-selected operations. You can put it by hand there. In fact, the fact that this property seems to be so ubiquitous around us, we've never seen a violation. I mean, I can understand that many people could think this actually maybe is a fundamental rule. But in this perspective that I presented, this is not seen as a fundamental rule. The difference is you say, okay, it's a boundary condition. And boundary conditions are these free data that somehow the theory does not specify to you, right? The theory tells you certain laws, but then there is these free variables that we need still we find out to be like that. And then we use them to make further predictions. And so, this makes, this leads to different, possible ways of what you may conceive is possible in this theory. So if you assume the standard theory where it is absolutely demanded that this is how it must be for pre-selected operations, then you have this unique deterministic effects in the future. And the only type of continuous continuous evolution that does not introduce noise will have to be the Schrödinger equation, because otherwise you're gonna end up with all the basically you can derive from this that your all operations you can conceive are trace preserving, the deterministic ones, and the pure ones is unitary. So somehow you need not postulate it separately. Somehow you can derive it under weaker assumptions. Whereas here there is no reason for that a priori. So this is more relaxed as I see it, because this is just a de facto boundary condition, which may be need it not be like that. And maybe it actually isn't even like that. It could be that maybe we just see it in our vicinity that it is like this, but in other places of the universe, you have something like closed time like curves. They are compatible. Certain models of closed time like curves, for example, are compatible with this model and with this rule. People have even proposed that but I'm not saying this is necessarily the right proposal, but like when you pass through a horizon in a black hole, suddenly you have this final state of the black hole that is like a post-selection, and that helps information escape. There are ideas, it may be that this need not hold. So, whereas if you believe in the other, if you regard this other constraint as part of the postulates of the theory, then you are not, if you kind of accept this theory and you work within it, you're not allowed to imagine these other things. So that's the difference I see. And I think this could be important, because maybe if we just restrict ourselves to this other way of thinking, maybe we could miss interesting opportunities.
Thank you. There are two other hands raised. First Andrea, then Lucien, and then there will be also questions in the chat. Andrea, if you want to go
Thanks,
ahead.
Pierre. Thanks, Adam, for the presentation. And I read your paper many times, and this helps me with understanding it more. I still don't understand one thing. That I think we disagree on something, but I'm not quite sure. Could you go to the last slide where you had the bullet points that summarize your points?
Mm-hmm. Oops. Here.
Oh,
yes.
There you go. So in particular, I'm not quite sure if I understand your points 1 and 4. So that the first one is that here, and Carlo was talking about, they asked a question about, and this other one is the boundary condition imply the memory arrow of time. Because, so the way I understand it, I understand quantum mechanics. I'm very, I like this idea of quantum mechanics is like both a way of model physical reality and a way of thinking of doing inferences, right? So there's kind of overlap between the two things. But I like to think of quantum mechanics mostly as a theory of inferences. So like, given I know certain things about the world, what can I infer about the rest? So this is very similar to the toy model you presented. Somehow part of it is like saying where the dots are and what values they can take, and the other part is the probabilities I assign to them, given what I know about certain values. Mm-hmm. And to me, it just seems that from this point of view, quantum mechanics, the boundary conditions, they basically represent, they encode your knowledge about the system. And then the rest is the inference. Then the circuit allows you to draw inferences from those to basically complete your knowledge. So you draw inference. So I put my state. The state is my belief system about the past, and then I can propagate that toward the future, and I can assign probabilities to events that are, other events about it, right? And so, from this point of view, basically the first thing that you call the theorem is basically a tautology. It's just like, if I don't remember the past, then if I have a state that is not a totally mixed state in the past, then I'm just saying I remember the past. And obviously the Born rule towards the past is not going to work. The same way, if I have not a totally mixed state in the future, the Born rule is not going to work towards the future, because I already assume I know something about the past. In other words, the Born rule is just a special version of the general rule for doing inferences that applies when I know everything about something from a moment in time to the past, or from that moment in time in the future, and I am trying to guess in the other direction. So in other words, like the Born rule works if I know the past and I try to predict the future, or it works if I know the future and I try to predict the past. And it doesn't work whenever there's like some mixed information about both the past and the future. So I don't understand if we disagree or not, because I agree with the first theorem just because I think it's okay. And so, so basically, but I think we disagree on what these boundary conditions mean, because it sounds like you think the boundary conditions are somehow objective, whereas I would say the boundary conditions are just what I assume I know about the system.
I agree that it is about what you assume you know, or what you assume, I would say. Perhaps just to be clear, that not to confuse knowledge, which is evidence-based and inferred, but to a belief. So
yeah, what I assume is prior knowledge.
So this question that you're touching upon is very, I did not include slides or questions in my presentation about that, but it's very important actually. That has to do with the distinction between which is the inferential parts of the theory and what is actually ontological in this theory. And I would not say that, and actually I don't know the answer to this question. This is the ground question of quantum mechanics, maybe, is to disentangle this. But I would not say that the boundary conditions I regard as ontological. Quite on the contrary, here in this analysis, I regarded them as priors, so they are somehow assumed. So at the same time, I regard them as boundary conditions analogously to classical mechanics, where they really mean ontological values, because just within the context of a theory, you have certain let's say, data or certain elements that enter in this theory that you use to make predictions for others. And so it plays the role of boundary condition. It need not be specified by the rules of dynamics. Like if you postulate unitary dynamics, it doesn't mean that you must have any specific boundary condition, yet you need one to actually use the theory. So in that sense, it's like a boundary condition. But I'm not sure, and this is what I would not say. I would remain in fact agnostic about this, but it seems to me I'm more inclined to say that in this context this is an assumption. So in a sense, I would not say that this makes us remember the future in some objective sense. rather, at least the analysis I presented, then the immediate conclusion is in fact that it's our assumption that we can remember the past that leads to the necessity to assign such a state, but it's a prior. And so, I mean, if you want to use consistently the theory, this is not something that's been inferred based on evidence. This prior need not be an outcome of a larger set of possibilities that would have been there. So in that sense, I would not, I do not think that it's useful to think of this as derived from the Born rule when you look back in time. I mean, the other is derived by calculating posteriors. Like we can derive this. If you start from the Born rule forward in time, you can, based on evidence, you can calculate posterior distributions. But when it comes to the reverse time direction, I don't think we have such a thing at hand. My analysis, at least, suggests more this direction where this is an assumption, in fact. But what I want to say is that if you want to be consistent in your usage of the theory applied on agents, of course, there are huge assumptions here. I treat an agent as a little system. They are macroscopic and so forth. But here I want to say, quantum theory, I want to apply the rules universally on everything, including agents. So I don't care about the details of this insanely complicated system. I will imagine that I could use the rules. So I model here agents by, I don't know, some, of course, the agent is still a little bit on the side, someone making the inference, let's say. But the thing is that if you want to consistently think about what is going on with you in particular, in the language of the theory, I believe this analysis shows that you need to assume a different prior. So you cannot say that there is this absolute validity of the Born rule back in time. That's whereas I feel you in your paper, you do say that essentially.
No, my point is that the validity of the Born rule backwards in time is conditional on the same conditions than the validity of the Born rule forward in time, namely that you don't know anything about the direction you're guessing.
But by knowing, I mean, this is a bit tautological. If all you're saying is that, I mean, a Born rule applies back in time when the state is maximally mixed. You may call it, I don't know anything about the system, or you may call it whatever. I can call it simply that the state is maximally mixed. Yes, this we know, this is true.
Yeah, and the Born rule forward in time only applies when the terminal object is totally mixed. Like as in, I don't have doing any selection.
As far as I mean, we do not know of it holding forward in time in any case, failing in any case forward in time. So here you may
because we don't have anybody who remembers the future. But if you were to just collect data in the Watanabe, like in the Watanabe setup, right? You run the experiment many times, and then you make inferences from the past to the future, keeping some information about the future experiment. The Born rule won't work.
Of course, but my point is that you are conditioning here on actual data.
Right. And when I'm doing the normal prediction, I'm conditioning in the past.
Yes, you are conditioning in the past, but if you do want to condition only on the future, on future variables, you don't get, if you believe that you are going to get the Born rule back in time, you're inconsistent in your beliefs that you have memories. That's what I'm saying.
Right, but the very fact of having memories means
that the initial condition is not maximally mixed, even as a prior. So that's what it means. It's not maximally mixed even as a prior. So it does not hold, the Born rule does not hold unconditionally on past events or past variables. If you believe
it depends what you mean by conditional.
Conditional is in the sense of conditional and probabilities. That's what I mean. Like that's why I had this slide on introducing, unconditional, conditional probabilities, priors, posteriors, because this is important. You want to condition on a physical variable or evidence, and it is based on this evidence that you.
But the Born rule doesn't work in the future in conditional either. Like if I remember the future, the Born rule doesn't work. So it's conditional on not remembering.
When I say it doesn't work, when I say it does work in the future, what I mean is that that as far as we can know, we we can, of course, this is what you're saying, it follows from what I said. If you, of course, if the future was different and we could remember it, which is, it would be necessary that actually the Born rule fails. If we could remember it, it's necessary that the Born rule fails. Yes, this is true, but we don't remember it as far as we know or as far as we believe. And therefore, it's consistent to believe that the forward Born rule holds unconditionally on future variables.
Okay, I think this is just a minor technical or verbal disagreement more than the substance. So I'll leave space to the other people that are raising hands. Thanks.
Thank you. Next one is Lucien Hardy, and then there will be Robert Okel.
Thanks for the talk. So I think this carries on with this discussion. So I didn't fully understand your proof of the first bullet point, but I think I believe something like that might be true, and it has to do with the fact that you have to, if you're going to actually verify some prediction, you have to do that locally at some point in space and time. So you have to transport, information. If you're looking at a conditional probability of, A given B, you have to transport B and A both to the same location, so you can actually sort of verify your prediction. And in the sort of framework that I developed, which is in some sense has a lot in common with the framework of Andrea and Carlo and Donna, there's a problem with that. If you want to actually transport memory about the past to the future, or memory about the future to the past, then really you'd want to set up a circuit that did that explicitly, and it turns out that's quite tricky because those, even the classical information in my framework at least, you have completely mixed noise coming in. You can condition on something in the past, but if you actually want to get that information about the past to the future, then you need another classical wire to do that. But that classical wire also has complete random noise coming in, so it's sort of impossible to do it. And I think you get you get into a problem there. And I thought a lot about how you would resolve that. And one idea is to try and sort of seriously model what it is that sort of humans are doing in that case, a kind of model and model it within the framework itself. And I sort of came to a possible conclusion that it might really be that we just have these strong beliefs about the past, but we don't necessarily have very good evidence for them. We just have these very strong beliefs, and that they're playing a very serious role. And I worry about that conclusion because if you take it really seriously, it's quite radical. It's this infinite regress that you mentioned, and I think that's a very serious problem. So anyway, that was my comment there. The other comment was so various people in the community have talked about how there kind of are two approaches to time symmetry in quantum theory, and so the people in particular are Giulio has a paper where he talks about that, the two possible approaches to time symmetry, and the two approaches are really sort of the sort of approach that you followed, and the kind of approach that Andrea and Carlo and myself have been following, and so Giulio's talked about this, and I think also John Selby has ideas along these lines. I'm not sure if John is in the audience here, and there are some very deep reasons for believing that. I haven't understood those arguments, but I thought it might be worth commenting on that and seeing if we could persuade Giulio to say something at some point along those lines. Okay.
Is Giulio in the?
I can see Giulio, yes.
Yeah, I'm here. I was listening. I mean,
it's very bad.
The connection is probably not very good, Giulio. We cannot hear you well.
It's very bad audio, Julio.
Yeah. Can you try maybe to cut your video? Maybe the audio will be better.
Uh-huh. Oh, I see. Yeah.
Yeah, Julio, are you
Lucian,
with us?
just to say in the meanwhile, thank you very much for your comment. Actually, I very much appreciate it. I believe what you're describing is the same idea that I was trying to convey. So, and I agree that the conclusion is very radical indeed.
Yeah, there's something to be understood.
It really points to really the deepest problems of quantum mechanics, really. Really what is out there and what is beliefs.
Maybe I suggest before Julio comes back that Robert Uckel, you can go on and ask your question.
Thanks. So first of all, thanks for your talk, Ognyan. So I want to make a few comments and questions at the same time. So in the past, I know we've been in general very much in agreement, and of course what you are saying here and this generalized version of quantum theory is very much in accordance with positive formalism and what I've worked on. But one statement that you had made had puzzled me previously, and that was when you were saying that the Born rule is time asymmetric, so I didn't previously understand how you meant this, but now this has become much more clear, and so maybe it would be a good idea if I say now the way I've understood it, because maybe also for other people this could be clarifying. Because I think there's also a thing that different people understand not exactly the same thing with Born rule. So okay, so the understanding of your use of this concept in this talk is now that basically what you're saying is with Born rule you refer to the linear in state and measurement rule for extracting probabilities, and basically so you're saying, okay, so this depends on the final state being the maximally mixed state, and if you reverse this in time, this is not working. Because in general you have not a time reversible boundary condition, or if you do want to impose this rule in the time reversed situation, then if I understood it correctly, what you're saying is that this implicitly means that you enforce the causality condition in time reverse. Is that right, my understanding? Is that when you're saying, okay, so now suppose that the Born rule holds unconditionally time reversed, that what you're saying, in other words, is that this means I'm really assuming the causality condition in time reverse.
Yes, the causality condition, yes. I would agree with that understanding that the causality condition is about pre-selected operations in that sense. So this is how it's actually non-trivial forward in time. Otherwise, I think trivial, but really what's non-trivial about it is that it holds for pre-selected operations. And so if we postulate that the same rule holds back in time for pre-selected operations, whatever that would be, that's equivalent, yes, to the statement that the initial state in the forward direction would be maximally mixed. I think this is true.
Okay, so so then I would say that yeah, I agree completely with what you're saying, except I would phrase it in slightly different words. But okay, I mean that's just question of nomenclature. So some more comments now, also maybe for the others. So this more general version of quantum theory is really about situations which are a bit outside of the standard situations, so it's basically the same what the positive formalism is saying. And in fact, I mean, when we were working on this, Ognyan and I, we were working separately, but in some sense, we did things in parallel and ended up with the same result in some sense, not formulated in exactly the same way. But so to strengthen the Ognyan's argument here about this more general version of quantum theory, so the necessity for, I mean, okay, as others have pointed out, in some situations, it is clear what quantum theory says about a situation where you have a measurement where you have both pre and post selection. And in that sense, you could think, okay, I don't really need anything beyond standard quantum theory. But if you go to applications where which are further away from standard situations where you have a fixed notion of time, then it becomes more obvious why you need this generalized version of quantum theory. So you can think of situations where you don't even have a predefined notion of time, and then you really don't know. If you just know the standard rules of the standard formulation of quantum theory, like the Born rule, then you have no idea how to talk about probabilities. And if you just naively apply a linear probability rule, as would be in Ognyan's example about applying the Born rule time reversed, then you're running into problems. So you do need a more general version. And this is what Ognyan was talking about. And as I said, if you go away from situations where you have even a notion of time, like which is maybe more easily done in the positive formalism, then you clearly see that a naive application of the Born rule would lead to inconsistent results. So one example that some of us here are familiar with is what Carlo and collaborators have worked on, this black hole to white hole transition. And so there I've described, for example, in a paper, how this more general quantum theory in the form of the positive formalism is to be applied. And the more general rule that Ognyan was talking about is in fact necessary to make sense of such a situation, which we expect to be common in context of quantum gravity. Yeah, okay, so this in respect to commons, and now I'd like to do a question. So for me personally, the most interesting part of the talk was at the very end. So I mean, if the others don't mind, if Ognyan could come back to the last slides he was showing us, with a little bit before that. Okay, so
do you mean about what was it about?
Yeah, so it was about what you're showing now, or a little bit before, because those slides
I don't talk about. This is interesting.
Very quickly, so I couldn't follow them. So when you had the space-time picture with Alice.
Yes. Okay. I understand this one.
Yeah. Yes. Exactly. So here, I think was very interesting what you're saying, but I didn't really capture it well, because so maybe if you can say more clearly what Alice is exactly doing and what she's making inferences about and what she has access to, then it could be could be more clear.
Right, so I'm saying Alice is performing, let's start from this assumption. Alice performs a quantum instrument on some input and output system, with some input and output system. So something rather, some standard operation, maybe even in standard quantum mechanics. Then by this dilation, we embed her in a unitary, and we say that the outcome, K, that she was observing, this distinct, in fact, after I purify, in fact corresponds to, let's say here, a projector, or could be a POVN. So it corresponds to this outcome of a measurement that we can now imagine applied kind of on the future of this time that we were talking about, right immediately after. So this is a dilation of the quantum operation. And somehow the idea is that, okay, I'm saying that this was an assumption that whenever I write down the circuits of the universe, let's say between two instants of time, all the experiments that are taking place inside the region between the two times must be mapped consistently on the boundary. But this means that this circuit that provides a dilation of these effective experiments that we do. So here I'm just, okay, I added a lot of things merely just as examples. I was just giving an example. Let's say that this is how we model her operation. So after I have evolved to this time, the initial state, it was not a state. If you remember, in general, I allow here even to have classical outcomes, just like here, like different labels for this classical possible outcomes. I mean, it's part of this way of thinking about quantum theory. So I use it all through. So here again, I've kind of imagined that I evolved it up to this point. And maybe you can think that this was evolved back from what was the future boundary condition up to this current point at time t prime. But I could evolve it back forward in time. And what would happen, of course, is that this projector or the system that was here, these operators, under the unitary evolution, they will evolve. They will get delocalized in general. They're going to spread over. But because at this point, I assumed that I have this picture where there is this local measurement happening on Alice. It is in a tensor product with the rest. This tensor product will remain a tensor product as I transform it unitarily. Just now, this is the transformed version of the P, and this is the rest. And so what we are arguing is now what we want to show is now the following. If the boundary condition is of the maximally mixed kind, namely the sum of these operators sum up to the identity matrix, I want to say that if this is Alice assumes that and uses her knowledge of the outcome PK to infer what will happen to other systems, and by infer, what I mean is that she should use the compositional rules of the theory. So in particular, she is applying a PK here. This PK, what it does, if you just follow it in this circuit, I mean, it passes through this unitary, maybe gets a little bit delocalized. What it does is going to it's going to hit, I mean, if you evolve it backward through this unitary, it's going to hit, let's say, these two systems, and it's going to project them. The actual outcome, if it's a projector, is going to project, let's say, this joint preparation into something else. And we know how to update operations. When you, like if you have a joint state, for example, if you project one subsystem, the other gets updated according to the knowledge that you have. So that would really all amount to changing this preparation here. So according to this knowledge, she should update her description of these states according to this information of the outcome. Nevertheless, this will remain unitary. The way you update this, but you update because you have direct knowledge about these boxes because she's directly connected to them. She does not change other boxes through this. You may do this, but you are changing the systems about which you're talking. So this would really amount to redefining the current preparation that she knows about for the rest of the universe. Then the rest of the universe will, of course, going backward. The rest of the universe will follow unitary evolution. these things that are other than the projector themselves, all these variables and operators that you can define, these algebras, they will follow unitary evolution. And then at the end, they will be hit by this final measurement. So I say, and this final measurement is independent of what she saw. So if this measurement is maximally mixed, essentially the circuit that she will infer for the future, for the other systems, apart from her own image, which is trivial, will consist of a preparation, some kind of preparation she can infer about the rest of the universe. So a set of possible states, maybe just one state, because very often we don't even consider these different outcomes. So it's a state, unitary evolution for the rest of the universe, followed by a measurement. And if this measurement is of the standard kind, then all the effective circuits that she could say happen in different regions, because by effective circuit, you know, the full circuit is one thing, but you can, for instance, say, okay, but I know that, for instance, this is until it's in the state 0 here. Like if you have some more, no, you can use the details about these operators here. This until it's in the state 0, so effectively these two are not going to interact. So I can just speak about this one as undergoing a independent, separate evolution, and I can define a circuit. All of these will be composed of standard operations because the full circuit that she infers for the rest of the universe is a standard circuit, unitary followed by standard evolution. Maybe, I hope this helps. I'm not sure. Please tell me if it helped you understand the issue. I realize this level of discussion is a little, maybe needs to be presented in much more detail. In fact, I take it as relatively obvious for people who work with circuits and know how to compose operations, but and we were missing this this was not part of our paper, and that's not actually correct how the argument was done there. Strictly speaking, it's not, let's say, wrong because you use the rules of the theory, but it doesn't make sense to make the assumption that we make. In the paper, we put the observer totally somehow in the box, let's say at one time. But then if this observer is really non-local in space, they could know everything that's in this box. But if I move the Heisenberg cut or below the observer, she would actually immediately know all the outcomes in the future. So it seems inconsistent to conclude that she could not know future outcomes because she would know everything. But that's if you're totally non-local. Whereas for any local observer, if they exclude their own image, everything else you would conclude to be standard circuits. So that's an important correction or improvement of the previous argument that I wanted to present.
Just one more question. So the measurement here is projected to the final time, or is Alice making a measurement and also the J's are measured at the end? I didn't get this part.
So can you phrase it again so that I can be sure that I understand what you're asking to reply correctly?
Yeah. So the measure. So Alice is making this measurement, but so you're thinking of the measurement taking place when Alice does it at t prime or at the final time?
Very good question. Actually, okay. So I'll tell you how I think. Alice is making the measurement at the interior time. So Alice, by definition, that I'm considering is here. So she's making the measurement at t prime. This measurement there, if you won't say that maybe somebody else is making it, or her own image into the future, which would be some kind of localized system, is making this measurement later. But I would not, and we, at the time of the first time we wrote this paper, it was not clear how to think, and I had this kind of heuristic ideas about some kind of holographic, maybe perspective, but actually I would not go that far. So I would say this is a measurement that is happening in the bulk, and it has its corresponding thing, the image in the future. If you think that there was an external observer who could come and actually place themselves right there, then they will see this other measurement that's there. So maybe, I mean, this is raising questions for interpretations of quantum mechanics that I think are very interesting, and this needs to be developed. For instance, I would not know what to tell you about situations in which, when you evolve back this measurement, it comes upon Alice in a kind of entangled form. And I'm not sure exactly how to deal with this precisely. But here it was an assumption that this is what is happening. Because quantum theory tells us measurements are possible, they do happen, but they don't necessarily tell us when, in which basis they happen. So here I assume that this happens in the bulk. I use the global circuit to consistently embed it. And then I conclude. But I think this direction is very important to be developed, and I don't actually know yet. There are ideas in progress about how to do this, maybe what you can maybe even say about reality, maybe you can give some kind of interpretations about quantum theory, but yes, it's...
But you haven't written down, you haven't written this down yet? And some...
These new modifications I have not yet written. No, this updated version of the argument I have not written, but I would like to write it, because first I would like to give a better version of what appears in that paper. And also I feel that some of the things I said, I personally found that maybe it could be helpful in actually understanding this issue, the distinction between prior and posterior probabilities. I think it was something that before I took for obvious and was never discussed maybe, but I feel that now this is an important conceptual distinction. When one makes it, one can rigorously speak about these questions. What do you know? What causes this? And so forth.
Thanks.
Thank you. There are still 4 questions. First, I would like to ask Giulio maybe to try to speak again.
Oh yeah, I just wanted to say that I am back, so in case we can resume the discussion that we had before. But maybe for this I would need Lucien to confirm what he meant, because he mentioned something of mine. I'm not sure I was understanding which paper he was referring to. If I understand correctly, this would be the situation that there are 2 different ways of looking at time symmetry in quantum theory. So one way is to say, okay, we keep causality, we keep the unique deterministic effect, the unique way to discard the system, and then we impose that we also have a unique state. So this would be, we make it time symmetric by keeping this uniqueness. So we have a unique deterministic state, typically the maximally mixed, but possibly something else. So this is one way to make a quantum theory time symmetric, by making it basically causal in both directions. Another way is more like the Aharonov approach, is to basically remove that constraint, both in the future and in the past. So you do post-selection and pre-selection. And that's more like what you do, Ognyan, with your extension of quantum theory, right? So that's my way of understanding things. I don't know if this was what Lucien was referring to. So for this, to continue to comment more, I would need to have some input.
Okay, maybe I should find the paper that I thought I saw these comments in, so I'll look and see if I can find it. Maybe that's a later discussion.
Mm-hmm. And just a small comment then slightly related to this. So this theory that you put together by following the framework of operational probabilistic theories and allowing for all these possible tests that are not allowed in quantum theory. Of course, this is a theory with the different operational features compared to normal quantum theories, right?
Yes.
So we all agree on this. So for example, if you have 2 pure states that are not orthogonal to each other, but linearly independent, in principle, these 2 states can be distinguished perfectly without any error in this theory.
In principle, yes.
Because yes, there is a particular type of experiment with the 2 outcomes that doesn't sum up to the identity. So it's like that would distinguish with 0 probability of error between any 2 distinct states.
That's correct.
So in this sense, if we look at it as seriously as an operational theory of experiments you can do, is radically different from normal quantum theory. So there is a lot of more stuff that you can do, and you retrieve only quantum theory when you say, okay, we restrict ourselves to a much smaller set of experiments. Right?
That's totally right. That's totally right. Yeah. Yes. Yes. Okay. Absolutely. And this is also helping me answer some of the previous questions, such as by Andrea, that indeed depends if you interpret it the way it's set up. I mean, it's much less constrained, so it is different. It's not quite the same as doing the Born rule. You would not come to the same conclusions.
Yeah. So this is one.
Although I think that here, I still need to just clarify that I still understand that Andreas' question was a bit more subtle than that. That this is kind of at face value, this is obvious, but one could still ask whether this is maybe just by allowing post-selection, then of course you can effectively by post-selection distinguish states and all that. So this to acknowledge that still Andreas' question was deeper than this, but yeah. So sorry, Giulio, go ahead.
I'm happy with that. I mean, that's all I wanted to say. Thanks.
Thank you.
Thank you. Then 3 last questions. First, Carlo, then Nick Huguet, and then Christy Stoika.
Think about, well, this last comment with Giulio threw me into total confusion. I thought I had understood, just I think now I'm lost. I'm completely lost. Let me make a comment. Maybe it's not a very popular comment in this community, but let me make it. I sort of don't recognize quantum mechanics here. Quantum mechanics is a fundamental theory we have today for doing physics. It's used widely in all sorts of contexts. And the situation in which there is Alice making a preparation, Bob making measurement or whatever, later in time, it's a teeny fraction of the context in which in current physics quantum mechanics is used. Quantum mechanics is used for accounting that the sky is blue, for understanding why there is nuclear reaction in the sun, how the sun works, how it's structure formation in the universe, for attempt to understand things, understand the early universe. None of this situation is of the kind, I make a measurement and I want to know what happened in the past, and I don't know what's going to happen in the past because it hasn't happened yet. None of this. And that's immense use of quantum mechanics. It's about processes. Some processes happen, some don't happen, some happen unlikely, some happen likely. And often it's used backwards. So my question is, for instance, let me zoom to a specific question. There is a big part of the community which is trying to use quantum mechanics for understanding what happened sort of before inflation, there was inflation, or in the early phase of the universe. And one way they usually work is that they have a clock time, so they find a way, it doesn't matter, that's not the point of knowing, having a time variable. They have a Schrödinger equation, they have a state that represents the universe now, and they evolve it backward. And from the evolution backward, they try to infer something that presumably has happened before, okay? With some uncertainty, and they claim perhaps uncertainty is less than what interests us. Now, my question is, according to you, they're just wrong because they're using Born rule backward, so it's wrong because we shouldn't. Are they already implicitly using your extension without knowing it?
It's a good question. I don't know, actually.
Or let me make another question. I understood from Giulio Cribella that this theory, it's really different than quantum mechanics. So what is a case in which we see quantum mechanics ahead here? What is the case where we see the difference? I'm a bit confused here. There is an ambiguity, so what we mean by quantum mechanics, okay? What is an extension of quantum mechanics? I do understand very well in which sense Robert Urkel works on extension in quantum mechanics, because his formulation of probability, I am tempted to say Robert Urkel is not extending quantum mechanics, it's just showing how to use quantum mechanics in a larger situation. But that's just language, usual language. So if by quantum mechanics, I mean Bob make a preparation in a lab and then Alice, or not the other way around, then of course everything is extension of quantum mechanics, but no, all physicists then do an extension of quantum mechanics. I'm confused. Are we talking about using quantum mechanics in a way which is not just make a preparation and make that? Of course, fine. We've been doing that for years in all sorts of, or are we doing, I'm confused.
Okay, so first, I don't know the answer about what you told me about these cosmological arguments exactly, because I'm not familiar enough to comment to know whether they're using implicitly or not some assumption about a prior state. But with regard to this, whether this is the same quantum mechanics and its implications for the universe, I mean, as I see it is, I mean, I had a slide which I kind of skimmed over, but is this thing I make this distinction, and this probably is very important. So when I started discussing this time asymmetry and forward, how I think about quantum mechanics, let's say, in general terms. On the one hand, you have this, what I would call quantum theory, which I understand in operational probabilistic rules, but it tells you something like the kinematic objects that you have, the main objects, and how to assign probabilities via some rules, what you can have. And then even if you take the standard quantum theory, it tells you, yes, you can have unitary evolution, for example, but it doesn't tell you which unitary evolution you necessarily have in the universe. This is given by dynamics. These are additional laws. You have symmetries, you have other considerations, some assumptions about the types of fields that exist in the universe and so forth, which are additional. You could have different types of universes that fit in the same framework. And then I would still like to some extent, I regard the dynamics could be seen as a sort of, when you view from the point of view of quantum theory, the dynamics is something that's given in addition. It could be this, it could be that, but then it actually is this one. In a similar way, what you have given, or you have to assume is given in order to use the theory, is to something like free variables or initial or final conditions in this case. Something that the theory is not meant to tell you what they are, but you need them, you need to say them, and only then you make predictions about other stuff. And so now, with regard to what Julio was saying about, for example, distinguishing non-orthogonal states, I mean, can we, the theory, well, first of all, we need to be clear about in which sense we cannot distinguish orthogonal states in the standard theory. Well, the standard theory is about pre-selected operations. So if we keep this in mind explicitly, then what we are saying is I could not possibly distinguish these states, with certainty without using post-selection. Or using operations that involve post-selection and things like that. So if you start allowing this type of things, but post-selection means that you go on into the future after you have done this and this and that, and you say, oh, now I succeeded in doing my operation. Right? This operation, yes, of course, it can distinguish certain states, but a priori, you did not know that you will succeed. And this is about the memory part. So you don't know that you will succeed. You need to go into the future to learn out that you actually succeeded. And a priori, you will assign a certain probability. So if you say I allow pre and post selection as such, you immediately somehow can distinguish, because with the post selected operations, you can distinguish these states. But it doesn't mean that the original thing is wrong. The original thing is still correct in the case in which the final measurement happens to be uniform. And so I would not say that necessarily this theory permits this type of things, but they need not be realized. Just like different Hamiltonians could be imagined, different initial conditions, but it doesn't mean that this is what is happening in our world. And when it comes to thinking about fundamental physics, like you said, Carlo, I think the way I think, you said I cannot recognize quantum theory in these operational formulations. And I can understand that. So for people who do really kind of high energy physics or field theory and so forth, the language is very different. But I find this as a kind of framework that you can understand in more imagining operational scenarios. You can understand the implications of field theories. And then of course, this is just toy models here. I'm using finite dimensional quantum theory, but you could conceive how this could be extended and what implications it may have for field theories. Like Robert Ockel is one of them. One of the consequences is this type of thinking. Is it different from the usual way? Well, if you take the quantum theory as defined, which is merely in the proposed approach, is just about prescribing probabilities given knowledge. You say what kind of things you can know about these boxes or regions, maybe regions of space-time. You say what is possible to know. It's possible to know maybe it's a unitary, it's a sum of projectors, it's this or that. So it tells you what you may know. And if you know that or believe that, and you know this about another region that's composed, the theory tells you how to calculate joint probabilities, but it doesn't tell you exactly what you should know. And so then comes the theory of dynamics that tells us what is going on if I take an isolated space-time regions and consider the fields that live there. The point is that because this theory a priori because it is more relaxed in the sense that it does not claim that you have certain constraint on pre-selected operations, it is compatible with different.
We're not communicating. It seems to me that you take quantum theory as its use, you restrict it enormously to say, well, that's what I mean by quantum theory, and then you say, well, I have to enlarge it again. That's what I perceive. Maybe I'm wrong. I mean, if quantum theory is used to understand the sun, and not because I mean, we look at the effects and we try to use quantum theory to understand what happened before what measurement, not after. It's
sorry. You can infer things.
Can I chime in?
Sorry.
Sorry. I think maybe I could try to clarify because I think maybe I have a better perspective on seeing both sides at the same time in some sense. Okay, so the first thing about Julia's question is really about, is that a different theory we're talking about here? And I would say it's really not. So what the difference, I mean, Ognyan and Julia were talking about, is what happens if you allow for processes that violate this causality condition. And then, of course, you can do things that in the normal framework you cannot do. But when we're talking about allowing such processes, this is also making a statement about physics, right? So if we understand this as a physical statement, as saying, okay, now I have a new theory that allows for more processes and they are physically allowed, so they occur, and then I can do things that I can't do in the standard theory. So that's one thing. But Ognyan isn't necessarily saying that, or I think Ognyan and I are really saying the same thing here, and so you don't need to do that. You don't need to say, okay, all operations that are allowed by the framework are automatically physically realizable. No. So if you say that, then you will find operations that are not compatible with or are beyond what standard quantum mechanics can do as we know it. But this is making an additional input. I mean, this is saying that, okay, I have this framework in which I express my physical theory, and now I allow everything that the framework in principle allows to be physically realizable. You don't need to do that. I mean, there's no reason to do that. I mean, you still have a physical theory that has specific state spaces, specific dynamics, and so on. And it might very well be, and as far as we know is the case in the physical theories we know, that these things do not occur there. So these things are not a prediction of the framework in that sense.
Very good. Now, so the question, this I understand exactly. So the question is that having quantum theory, which allows us to, given the past, predict the future, given the future, predict the past. If you have knowledge of something, I can infer something in the past.
Okay, so let me go to
rest or not. I mean, it's two different things, right? It's a.
Okay, let me also try to say something about this. So also what Ognyan was saying at the beginning of his talk was, okay, so in the standard formulation, we have this causality condition, okay? Now, what happens if we want to relax? I mean, what he was saying could be seen as the consequences of what happens if we throw this rule away and making inferences so one way of reading what he was saying at the beginning, he was using time reversal to achieve this, but you could also achieve this in other ways, you would say, so what happens if I throw away this causality rule? And he's basically saying the conclusion is it will be inconsistent. Okay, the linear probability rules of the standard formulation will be inconsistent if I throw away the causality rule. So the way he was expressing is what was using time reversal, because in reverse time, the causality rule doesn't apply in the standard formulation of quantum theory. So, and he was saying, okay, so now I get problems. This is not consistent, or I cannot have memories, or I mean, there are different ways to say this. So, okay, so let me now add from, let's say, my perspective, what I would add to that is that, so in the standard formulation of quantum theory, the causality condition ensures that the standard Born rule gives consistent probabilities. Now, if I throw away this causality condition, then the standard Born rule is not necessarily consistent anymore. In fact, it doesn't give consistent predictions in general. And so there are situations, now coming back to more concrete physics, where it is necessary to throw away this causality condition. And this is precisely when we don't have any fixed notion of time anymore. Okay, in that situation, the causality condition doesn't make sense. It cannot be consistently formulated because it relies on a partial order in time between processes. If this doesn't exist, you cannot consistently impose this causality condition, and with that, you throw out the standard Born rule. It also will not be consistent anymore. So you need a more powerful, more general framework, which still works in this more general situation. And this is precisely the framework that Ognyan is talking about. And it's also precisely the positive formalism in its essence. Okay, so sorry, I shut up.
I understand what you say. I'm not sure I agree. Namely, I mean, I understand that one can. I mean, what is in our paper, and that's, I would say, Andrea, key contribution, will just clarify so many things. It's like, it's causality condition admits a time reversal invariant version. I'm not going into technicalities here. So you can keep it, stay within what I would call standard quantum mechanics. So that's just terminology, and have a time reversal formulation, and not violate the causality condition when you're asking question about the future given the past, and having exactly symmetric condition when you're asking question about the what happened given what you observed today. So that's a subtlety. Is it needed to go to a larger? Robert, you're doing something else. You're extending quantum mechanics to the case where there is no T. Okay, that's obviously, if you want to call it an extension, it's an extension. And that's very good, very fine, I understand that. I don't understand why, just because we have what seemed to me something which is already in the quantum theory and to others, which is time reversal invariance all the way through, okay? Only broken by the kind of questions that we ask to the theory, why allowing more general questions necessarily would bring us to this possibility of larger set of phenomena. And this is about quantum mechanics, not about the specific Hamiltonian and anything. I'm assuming a self-adjoint Hamiltonian, and so time reversal invariant of the dynamics. But I'll shut up. I've been talking too much, so I'll close my microphone because I've talked too much. Sorry.
Thank you, Carlo.
Do you want to answer something to this, Ognyan?
Can I just make maybe a quick comment? Just to reassure Carl. I mean, the operational approach that the one that Ognyan refers to is not really any different from the quantum theory you are familiar with. I mean, the one that we learned that the states we can prepare are the vector of unit lengths. The evolution is unitary matrices, and the measurements are a bunch of projectors that sum up to the identity. I mean, that's what we are talking about. I mean, the operational formulation is just bringing these to kind of the fact that you can have mixed states, measurements that are not projective, but it is a consequence of this and nothing more. So in this sense, maybe the jargon may be a bit confusing, but we are really talking about the same thing here. That was just a quick comment. Yeah.
Yeah, thank you. No, this I appreciate. Sure, thank you.
In this, I would just like to add that for me, these operational reconstructions that you and others have developed, Lucian, and many other people have tried. I mean, this helps also understand what the theory is about, let's say. I mean, not really the ontology about it, but even how, when you do theory building in this context, for example, this apparent non-contextuality of this modified rule. I mean, you think, okay, why do I expect this non-contextuality in the first place? And when you start thinking, I was very excited to learn this from your papers, Giulio and Lucian. I mean, you see that you understand that this makes sense because you take equivalence classes, and then you come to this time-symmetric theory, and you can actually understand that it's completely normal that things look like that if we started from this other theory here. And that's okay, there is no problem. And here this theory is non-convex, which seems very bad. But on the other hand, if you take the philosophy in mind, which is that you would like to just talk about, given local knowledge about this and that, how do I combine it to predict joint probabilities, and you want to update this knowledge, if you allow this possibility, you automatically have to have this thing. Of course, you can conceive these mathematical convex extensions, but somehow they don't quite correspond to local operations. But this is okay, all of this is okay, and I found this also particularly insightful. Also, when you start thinking about quantum field theory in Robert Ockel's approach, I mean, how do I interpret it? Everything looks the same somehow. In which sense is that the same, really? When you take the perspective that it's all about information and events, I think this kind of elucidating. So I found this way of thinking useful, but one need not. I believe it could be translated to usual language, and actually the bridge is provided, I think, to Robert Ockel's quantum field theory approach.
Thank you. So unfortunately, Nick, you had to go, but Christy Stoika, if you want to ask your question.
Nice talk. Thank you very much. I probably should read the paper and maybe then contact you. This is why I decided to lower my hand. But just based on a few things that I think I understood, I have the feeling that you can basically arrange any sort of this kind of situation that you describe in the talk by using enough post-selection. Am I right? Or
yes,
I mean, like, for example, yeah, please.
I think the answer is yes for smaller systems than the full universe.
Yeah.
Then I believe, as far as we know, you could realize all of that with post-selection. All of these are, in some sense, also occur, if you like, but they don't occur unconditionally. They occur conditionally on certain variables, usually in the future.
So in some sense, I think, although it's a different framework that somehow seems to do interesting things, I mean, unusual things with causality, but looks to me like it's just, I mean, not just, but it's basically quantum mechanics treated in a very interesting way. Pretty much like the two-state vector formalism, but in which you have more freedom, so to speak, to choose the past and the future, I mean the post and the pre-selected. And also what I find interesting is the Born rule part. And the fact that you need to have the state to be maximally mixed makes me ask you if this can be related to a paper by Bob Kweke and Gojose and Selby, the time reverse of any causal set theory is eternal noise.
Yes, I like the title. Very.
Yeah,
Yes,
they use the diagrammatic formalism, and but I think
that's the idea. Of course, if you time reverse the past condition and you put it in the future, you basically get still the same thing. You just go to the future past and the past future, but it's still a non-trivial theory. But if you put it on both sides, then as I tried to argue, it's essentially eternal noise.
And you can have probably something mixed, like somebody linked a paper with by Czeslaw with a superposition of two different thermodynamic arrows of time. So thank you very much. I loved it. Okay.
Thank you for your comments.
All right, since that we are done with the questions, there were also other questions in the chat, but since it's more than 2 hours that we are discussing, I suggest that we close the session for today. And Ognyan, I can, if you want, record the chat and send you a copy of it if you want to read everything which was commented and asked. So yes, thank you again, Ognyan, for your participation. Thank you everyone also for all the questions and discussion.
Well, thank you everyone for your interest.
And we see each other in 2 weeks for another QISS virtual seminar with Faye Doker, who will be speaking. All right. Bye, everyone.
How do I stop this share finally?
So I'm trying to record the chat for you, Ognyan, but I've never done this.
Okay, so I will try to copy it myself as I see it right now, and I will paste it because I also clicking on a file, somehow it doesn't come. Like, Dropbox, maybe, yes. I will just probably copy it and then I'll read it later. Thank you very much.
Yeah, are you able to copy everything easily? Or?
It's going slow. It's going slow right now. So
yeah, because normally there's an option which is save chat, but when I click on it, and I mean, I don't know where it's recorded. Like there are 3 dots, and if you click on the 3 dots in the chat,
yes,
you have the possibility to make
there are
save
options.
chat.
It says something like Dropbox and etc. Let me see if I can, if I paste it